The roadmap here is we're going to learn very soon about average velocity and average speed. And then we're going to talk about average acceleration, and then we'll talk about instantaneous velocity, instantaneous acceleration, and then we'll start calculating how things move using equations that relate all those things together. But it all boils down to what we learn here as a foundation, because there is a difference between position and displacement and distance that's going to carry through into the follow-on lessons. The good news is it's very simple to understand, all right? Before we write anything on the board, just know that everything in this lesson is really concerned with one-dimensional motion. When I say one-dimensional motion, I mean that imagine there's a string right in front of my eyes here, invisible string, and there's like a bead on that string. And that bead can only go back and forth across the string. It can't go towards you and it can't go up. So one-dimensional motion is just back and forth. We call it along the x direction. Later on, we'll bring the y direction into it, and then you can have complex motion like throwing a baseball. You bring the z direction into it, and then you have freedom of movement all around, okay? In this lesson, we're talking only about one-dimensional motion, so one-dimensional distance and displacement and so on. So let's first talk about the concept of position. So if we're going to measure something's position, then we have to have some framework, right? So you may have remembered, or you may remember from grade school, we learned about this thing called a number line. And a lot of students say, why do we care about this number line? Well, here's a good example. We're going to use that number line right now. Here, we're going to talk about the position of something, and we're going to call it in the x direction, and we're going to be measuring meters in the x direction, meters away from the reference point. Now, I'll just pause for a second and tell you that every problem you work, every problem has to have some sort of reference point that everything is measured in relation to. Now, because this is only a one-dimensional motion, we have the 0 point on the number line. That is the reference point. In two-dimensional motion or two-dimensional problems, you have an xy plane, and the origin at the center there is the reference point. And then we have a similar reference point for three-dimensional motion as well. So everything is measured relative to this. And as you probably remember from grade school, when you go this way, you have positive 1 meters away from the origin, then positive 2 meters from the origin, positive 3 meters from the origin, which is just the number 0. Going the other way, we have negative 1 meters, negative 2 meters, and negative 3 meters. Now, these negative numbers, they're not like mystical things, okay? If you see a negative number, all it means is it's 1 unit away from the origin, but we're defining positive distances to be to the right of the origin, and we're, because of that, saying that negative distances are what exists to the left. So a lot of students, when you start solving problems, get very confused. What does it mean to have a negative distance? What does it mean to have a negative position? Isn't that weird? Well, no. If you have a negative position, it just means you're on the other side of the 0 point, right? And so just like in the xy plane, we'll get to this later, when you have negative positions, you're maybe down below the ground or something, because the origin might be the crossing point of where the ground meeting, where you start to kind of go up and throw into the sky. Down below, the lower part of the xy plane might be below the ground or below sea level. If we're talking about a submarine, going down might be negative distances below the sea level of the waves, right? So the negative numbers on distance or displace or any number you calculate should not worry you. They just mean, and they're telling you some information. And this information for position means that you're that many units to the left of 0. Positive means you're that many units to the right of 0. So if I mark on this thing some position at this location here, I call it A, and then some position over here at this location B, then the first thing we're going to talk about is the concept of position, right? Position. So what is the position of point A? The position is just the coordinate locating its the location of that thing. So when you say, what is the position of a baseball, all I care about is the coordinates of the baseball. Now, because this is only in one dimension, there's only one coordinate, the x coordinate. But when we have a baseball in 2 dimensions flying, then we'll have an x and a y coordinate. That all comes later. We always first learn motion, and we learn how things move only in 1 dimension first. Then we tackle 2 dimensions because it's more complicated. So for right now, the position of this particle, if it can only exist in the x dimension, in the 1 dimension here, the position is at x is equal to, I'll call it x is equal to negative 2. Negative 2 what? Well, it's negative 2 meters. That means it's just 2 meters to the left of the 0 point. And the position of point B, you can see similarly, it's just an x coordinate and it's 1, 2, 3 units, positive 3 units, 3 meters to the right. And the implied positive sign here just means it's 3 units to the right. So you see the sign carries information. A negative sign means it's going one way from the origin, and the positive means it's going the other way. So the negative and the positive numbers that we learn back in algebra and pre-algebra, they become very important in physics because, you know, a negative angle, a positive angle might be up, a negative angle might be down. It just means it goes down below the 0 point, right? Throwing something up might have a positive, you know, a positive value for its height, but a negative value might be just something that's down below the ground. Maybe it fell into a canyon or something like this. So this was the position. Position just means give me the coordinates. Now we have to talk about something called the distance traveled. We all have an idea of what we think distance traveled means, right? If I drive in a car, the little numbers go ticking up in the instruments and it tells me how far I've traveled. You fly an airplane, it tells you how far you've traveled. The GPS tells you how far you've traveled. Distance basically means along my journey, if I add up all of the back and forth, up and down, no matter where I go, all of the entire distance that I've traveled, no matter which way I'm going, even if I backtrack on myself, I'm still adding up the total distance. That is what we say when we mean the distance traveled. It means everything. This way, this way, this way, this way. I'm adding everything up. That's the total distance traveled. So if I'm talking about distance traveled, right? Then a good example of this is to draw another coordinate, another x dimension like this. So again, we're only talking about motion in one dimension along the x dimension. Now I'm going to put this 0 point back in place. And then we're going to say that we have, just like before, we have 1, 2, 3 to the right, 1, 2, 3 to the left. Of course, the numbers keep going in, going forever. -3, -2, -1, 1, 2, 3. All right, now let's say that I start some journey right here. And I'm going to put the dot right here, and that's going to be the starting point, and the ending point is going to be over here. But what I'm actually going to do is I'm going to draw it in a little bit of a different way. I'm going to put the A up here. I'm going to put a little dot here, but it's really the same dot. I'm just drawing it up because you're going to see why in a second. Let's say that for this particular journey, remember, we have a string here, and I'm like an ant on that string or a bead, and I literally can only go along this string, either this way or this way. I can't go up or down. I have to go along the string. So I start here, which is right here, and I travel. Because I don't want to scribble over my lines, I'm going to show you like this. I travel to the right here, and then I backtrack and go right back to the starting point like this. And then I go again towards the finish line over here, and I stop here, and then I go back here. And then I go all the way over here to point B. Now it's important for you to understand that even though I've drawn it kind of going down, it's just because I didn't want to scribble over myself. If I start here, it will be the same thing as going this way and then back, and then all the way to here, and then all the way back, and then all the way here. You see, because I can only travel along this string, but I'm saying I go a little bit this way, then back, then a little bit more, then back, and then back to the actual finish line. So if I ask you, what is the total distance traveled between A and B? What is the total distance traveled as I journey from A to B? Well, you can count it up. And if this is in meters, I traveled 1 meter here, and then there's 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, 7 meters, 8 meters, 9 meters, 10 meters, 11 meters. That's the distance traveled. One more time, let's try it. 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, 7 meters, 8 meters, 9 meters, 10 meters, 11 meters. That's the distance traveled, right? Notice that I went back and forth, and I included the distances going back and forth in the total distance, but no matter which way I was going, I didn't really care about negative signs or positive signs when I add up the distance. In other words, when I'm going this way, it's like traveling in the positive direction, but when I backtrack, it's like I'm going in the negative direction, but I still treated these backwards paths as positive distances. So basically everything counts as a positive number, and so the total number is 11. Basically for the distance traveled, you always get a positive number. The distance will always be positive. So distance, always positive. Positive, that's what POS, positive. Distance is always positive because if I go this way, and then I go backwards in the negative direction, I'm still counting it as additional distance. So there's no way you can have a negative distance. You basically always have either zero distance, and you don't move at all, or no matter what your path is, you're just adding up positive numbers, right? So that is what distance is. It is adding up all of the little segments along your path. If I had an XY plane and I had two-dimensional motion, I would go up and down and up and down and back. I would be adding up all the distances. No matter if I was going up or down or left or right, all of them get added. And that's what your car records. When you are looking at the odometer in the car, it's the total distance traveled, okay? Now we have to contrast this with the important concept of displacement. We all know what position is, usually before physics. We all know what distance is before physics. But displacement is something we don't usually learn about until you get to physics. And a lot of students think that displacement is the same as distance, and it's not. But the good news is it's very simple to understand. So let's go and talk about, on the next board over here, the concept of displacement. First of all, what do you think the word displacement means? Displacement is a word that means, it means to move something and to change something from some initial position to some final position. To displace something. If I go to you and I displace you, it means I bump you out of the way and you move somewhere else. Or if I'm in line and someone displaces me out of line, I've moved out of line or to a different place in line. So to displace something is to move it, but really I only care about the final position and the initial position. That defines the displacement. So the displacement is calculated by delta, which is a triangle x, because we're talking about the x direction, right? And this is equal to x sub 2, and then we're going to subtract x sub 1. So let's talk for just a minute about this, because a lot of students look at this and get confused. When you see a triangle, triangle means change, right? So anytime in physics you see a triangle, it means change. So literally, not chance, change, sorry about that. So if you see triangle x, you literally read this as delta x, but in your mind, it means change in the x coordinate. That's what it means. How did the x coordinate change? Now, how something changes in general means that basically you look at the final resting place of where it landed, and then its initial place where it started, and the subtraction of those two things tells you how that coordinate changed. The displacement of the thing is how the coordinate changes, and it's only concerned with the final. When you have a number 2 there, that means the final position minus the initial position, right? But notice that it only depends on the endpoints. It only depends on where I start and where I end. It doesn't have anything to do with any backtracking or zigzagging or anything like that that happens between the start and the end. It only matters how I started and how I ended. And that is the main difference between distance and displacement. Over here in in distance, notice this was the start point and this was the end point, but I'm adding up all of these extra distance because I'm backtracking in the total distance. Whereas the displacement only cares about the end points. Where did I end up? Where did I start from? Subtract them. That is the net displacement. All of this intermediate zigzagging, it doesn't matter at all for displacement. Only the start, only the end. That's why we take the ending point and we subtract the starting point. All right? So let's take, for example, the following. Let's draw a little picture. And we'll take, it'll be very simple. So here's 0. And we'll go over here and we'll say, all right, 1, 2, 3, and here's -1, -2, -3. So -3, -2, -1, 1, 2, 3. All right, so let's say then that position A was right here. This is the starting position. And position B, the final position over here, was right there at these coordinates. Now, the coordinates are given by the graph, so we know that we can then calculate the displacement. We know we start from A and we go to B. So we can say that the displacement, the change in the x coordinate, is equal to x2, the final position, minus x1, the initial position. So the change in x is, what is the final position? This is the final position, x is equal to 3. Minus, what is the initial position? The initial position has a coordinate of -2. you're going to be subtracting, but the coordinate that you're subtracting is itself negative. So you're subtracting, and you need to wrap this in parentheses, -2, because that is what you are subtracting. And we all know from algebra that double negative like this means positive, and so delta x is equal to 5 meters. Now, does this make sense? What it's basically saying is the displacement, the change in the coordinate from initial to final is 5 meters. And that's exactly what this is. If I look at this, it's 5 meters. You can see 1, 2, 3, 4, 5. Now, because we got a positive answer, there's an implied positive answer. Positive means moved to the right. Remember, I told you that the way this was set up, we have to have a 0 point. And this direction is positive, this direction is negative. So when I calculate a displacement like this, that has a positive answer, that's 5 meters, there's 2 parts of it. The first part of it is that there's 5 meters of travel. And that's important. That's what we call the magnitude of the number. But the other part that's important is the direction. And the direction is given by the positive sign. The positive sign here tells me the direction that I moved in this displacement, and I moved positive to the right like this. I think it'll be a lot more clear when we do the next problem. Let's do the next problem, and you'll see how you can get a negative displacement and what the difference means there. So let's see, for the next problem, let's do the same sort of thing. Let's go and draw the number line again, and then what we'll do is we'll put everything down just like we did before. There's the 0 point. Here's 1, 2, 3, and here's -1, -2, -3. So -3, -2, -1, 1, 2, 3. This is the x coordinate, and it's in meters. Now notice that over here, when I said the displacement from here to here is 5 meters, notice that I don't care the path that this particle travels. In other words, just like we showed here, there could be zigzagging going on. Like the particle could just start here and go straight to B. Okay, that's a displacement of 5 meters. The particle could go here and then to 0, and then back to start, and then to 1, and then back to 0, and then to 2, and then back to 1, and then back to -1, and then back to -2, and then over here to 2, and then to 0, and then finally it ends up there. You see how there's a bunch more steps there, but the displacement doesn't care about the steps. The displacement only cares about the final position and the initial position, 5 meters. That is how distance and displacement are different from each other. Because when I calculate the distance, I'm going to add up any possible zigzag along my path for the total distance on the path as I move in the journey from A to B. But when I calculate the displacement from A to B, I don't care what I do in between here. The displacement is only the net result of the start to the finish. In other words, the displacement only cares about how I've moved as a net result going from start to finish. Any zigzag, backtrack, none of that's counted. It's only the final resting place and the starting place. That is the displacement. The sign of the displacement tells me my net movement, positive 5 meters to the right. There's a magnitude, 5 meters, and a direction to the right, right? But I don't care if I zigzagged or whatever. It's only the net movement from start to finish, right? If I went back, and back, the distance might be 20 meters, but the displacement is only relevant from the start to the end. Now let's go and do our second example. Let's say in this particular example that we actually start over here at 1 here, and I'll put this as A. And we finish over here at B, so I'll put the little dot right here. So we finish over here at B. But just for giggles, let's go ahead and show the path. Let's say I start at A, and I go here, but then I backtrack and I go right back to the starting point. And then I go all the way over here, and then I backtrack here, and then finally I land right here, which is the ending position. Now, I just drew it like this because really what's happening is I don't want to backtrack on myself or you won't be able to see it. I went here and then back, and then I went here and then back, and then I went finally here. Now what is the displacement here? The displacement is delta x. It only cares about the ending point, the final position, and the initial position. It doesn't matter any of these zigzags for the displacement. So for the displacement, the final position, B, is -3. And we're subtracting from it the initial position is +1. And from algebra, you know that this is equal to -4, and this is a unit of meters. This is the displacement -4 meters. What does the negative sign mean? Well, if positive means move to the right, negative means I moved a net distance to the left. And look at see if it makes sense. If I start here and I end here, I moved 1, 2, 3, 4 units, and I moved to the left, because in this situation with this graph, positive is indicating, in other words, increasing values of x go this way and decreasing values of x go this way. So if I get a negative number, it means I must have moved to the left. And if I get a positive number, it means I moved to the right. But notice the distance is actually different than the displacement here, right? The distance would be 1, 2, 3, 4, 5, 6, 7, and 8. I believe it's 8. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8. So the distance actually would be 8 meters, because sometimes you backtrack, right? But the displacement doesn't count any of that. It's only the ending and the starting. But again, one major difference. The distance will always be positive, always, because you're just adding up numbers, no matter if it's left or right. It's just a number, right? The distance is just a number and it's always positive, but the displacement can be negative and it could be positive. There's two parts of this thing. The sign tells you which direction you're moving, and the number tells you how far you moved, right? So that's an important thing, because most of this class will be concerned with something we call a vector. We're going to talk a lot more about vectors. Vector. A vector is a very, very, very important concept in physics. It has something called magnitude, and it has something called direction. A vector has to have both magnitude and direction. It has to have both of them, or it's not a vector. So the displacement is actually the simplest vector we're going to talk about. And we're going to talk about a lot of different kinds of vectors. There's many, many kinds of vectors. Anything that has a magnitude or a number associated with it and a direction is what we call a vector. This one's a vector because it has a magnitude of the distance traveled, and also the sign tells us if it's left or right. So it has magnitude and a direction, it's a vector. But there are other vectors. If I throw something and I talk about the velocity, we're going to talk about velocity in meters per second very soon. I have a magnitude, that's how fast I'm throwing it, and the direction could be the angle that I'm throwing the thing. Magnitude and direction, that's a vector. Velocity is a vector. Acceleration, we'll talk about acceleration very soon. That has a magnitude and a direction, because I can speed up or I can slow down. It has a direction as well. And so acceleration is a vector. But I can go beyond it. Force, when I push on something. When I push, I'm going to push with a magnitude, how strong I'm pushing, and the direction that I push. Maybe I push down on it, maybe I push up on it. The force that I push is a vector, because I can change the angle that changes the direction, right? What else? Electric fields, magnetic fields are all little arrows that point, and they have magnitude, they have direction. There's many, many examples of vectors. The opposite, or the other term, things that are not vectors are just numbers. They're called scalar quantities. And we'll talk a lot more about scalars later, but scalars are just numbers. They don't have any direction. So for instance, the temperature in this room. At every point, there's a temperature in this room, but the temperature has no direction. So it's not a vector, right? The things that have magnitude and direction are called vectors. So we're going to get into that a lot more a little bit later. Our simplest vector is called the displacement vector. All right, the last thing I want to leave us with is, in this lesson, we've only talked about one-dimensional motion, because that's where we're going to start studying motion. But I do want to talk a little bit about two dimensions here at the end, because it's very important. It very much helps us understand, again, the difference between distance and displacement. So let's talk just for a second about two dimensions. It's very, very simple. In two dimensions, everything happens in an XY coordinate plane. In three dimensions, you'll have X and Y and also Z, which would come out of the board. So here we have X, which you can measure in meters, and we have Y, which you can measure in meters. Now let's say that in our grid, we have two little markings here and two little markings here. And this is like, 1 and 2 and 1 and 2 meters. So this is 2 meters up, 2 meters over. Let's say that I start walking in a city, in some sort of city right here. So I'm going to put A right here. And what I do is I walk north 1 meter like this, or 1 block, or whatever it is. I'll put a little arrow here. And then I walk east to the right, again 1 block, down 1 block, which is south, and then I walk right back to my starting point. And so what I'm going to do is I'm going to put B right here also, because A and B are right on top of each other, because I ended up where I started from. So in this type of situation, what would be the distance? What's the distance? Well, I started here. I went 1 meter. Here's another meter. Here's another meter. Here's another meter. So my distance is 3. Whoops, not 3. I can't even add. Is 4 meters. Why? 1, 2, 3, 4 meters. But what's the displacement? The displacement, we're going to learn how to calculate displacement in 2 dimensions, but I think you can see the displacement is 0. Why? Because the definition of displacement is its final position minus its initial position. Now, yes, this is just for the x coordinates, but it works. We'll give the equations later, but it's going to take into account x and y later, but it's still the final position minus the initial position. But if I start in the same place that I end, then I have not moved any net distance at all, then the displacement's actually 0. Because if I literally do walk, 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 and walk, and literally if you close your eyes and only observe me at my starting point, and then you open the eyes when I get back to the ending point, it appears that I've not moved at all. My displacement is 0 meters because it only matters where I start and where I end. That's displacement. Distance is the whole enchilada. Any intermediate movements, and distance is always a positive number, and displacement, as we just said, can be positive or negative. So here, we've conquered quite a bit of stuff, actually. And it's very, very important stuff because everything builds on it. We talk about velocity and acceleration. All of that builds on this. Position is just a coordinate. It's where are you, right? So positions are just coordinates. X is negative 2 meters, or x is equal to positive 3 meters. Distance is when I start traveling and I add up all the distances. Even if I backtrack on myself, I add them up, so I always get a positive number for distance. Whereas displacement, even if I have these intermediate zigzags going on, all I care about is the final position minus the initial position. We talked about the delta notation. That means the change in some coordinate, final minus initial. We might have delta x for position. We might have delta t for temperature. Final temperature minus initial temperature. I might have delta, who knows, delta density, right? Final density minus initial density. In general, the Greek letter delta we use to mean change in something. Final minus initial. So go through this again, solve these yourself, make sure you understand the difference between the position of something, the distance something travels, and the displacement. And the most important thing I want to drill home here is that displacement is important because it's a vector quantity. There's 2 parts to the displacement. There's the number, which is the magnitude, and there's the sign of it, which tells us which way we move. Magnitude and direction, that's called vector. Here we got a negative number, and here, for the displacement, we got a positive number. The number means something. The sign also means something. That's a vector quantity. We're going to talk about vectors for like the entire class, so I'm really kind of harping on it right now. So solve these, follow me on to the next lesson. We'll continue to build your skills. Learn anything at mathandscience.com.